All right, so first, let's review the goal and learning targets. That tells you if you were successful or not. And then, so the goal today was to investigate what graphs can tell us about the equations and the relationships they represent. So another main thing was the two different forms. So it was the same graph, even though it's two different forms of the equation. And each equation showed different things. So, for example, one of the equations was in this format. The ax plus by equals c. Does anyone remember what that format is called, by the way? I said it, but like just once, I think. So it's ax plus by equals c. What do we call that? Yes? No, good try. That's something. At least a response. No. Anyone else want to give it a shot? Can someone tell me what the other form is called? Or what the equation for the other form is that we talked about today? Yes? Okay, good. So y equals mx plus b, this one's called slope-intercept form. Anyone know why it's called that? What two things can we see really easy when it's in slope-intercept form? The slope is one of them. Which of these would be my slope? The m, so slope is m. What else can you see really clearly from slope-intercept form? Also in the name. The intercept, Brian?
The y-intercept.
The y-intercept specifically. So, and which letter would be for my y-intercept? It's a good guess, but no. It's gonna be the v. Okay, so that's gonna be my y-intercept. So the two things you can see really clearly from slope-intercept form are your slope and your y-intercept. X and y could be inputs and outputs, but usually we just leave it as x and y when we're graphing. Okay, so that's slope-intercept form. This over here, ax plus by equals c, is what we call standard form of linear equations. Because all of these make straight lines. And that's what this unit is our linear equations are straight lines. So standard form, slope-intercept form. We already talked about what you could see really easily in there. What do we usually use this equation for? Think like the warm-up today. Think like what those equations talked about. I can even show you them again. Right, so let's see. All right, so like here's some. They're all in standard form, aren't they? Ax plus by equals c. John? You could graph using this, albeit it'll be different than when we use slope-intercept form. So like you could plug in values, yes, you can, but specifically you could see if it's a word problem, like this is probably the equation that you will come up with. Like it's less likely that you come up with y equals mx plus b. But if they're talking about like how much something costs and the total of it, it's probably going to be something like this. Okay, so the relationship you could see is like how much the games cost, how much the rides cost, what's the total spent. That's what you can see from standard form versus slope-intercept form where you can see the slope and y-intercept. So that's like what I was going for. All right, so there's pros and cons of each form. You still have to be able to graph no matter what form it is. And we just barely touched on that today. So if it's standard form, I recommend finding your x and y intercepts. And we didn't explicitly say this during the lesson, but maybe you noticed it. Let's see. Hold on. So like, here was some of the examples we did. Although we didn't say it during the lesson, what we were solving for in number 1 and number 2 for each graph was our X and Y intercepts. You solve for plugging in 0 for either the X or the Y, and then solving for the other thing. So like this right here is my Y-intercept, it would be on my Y-axis. That coordinate was 0, 15. Because your Y-intercept is when X is 0. Your X-intercept, which for this one was 6, 0. Your X-intercept is when Y is 0, right? And that's how we solve for it algebraically. So you could graph by finding your X and Y intercepts and then just drawing a line. Or you could graph, if you know your slope-intercept form, by plotting your, let me find what slope-intercept form. So like this would be in slope-intercept form, for example. By plotting your Y-intercept, and then using your slope, your rise over run to find your next point. All right, so there you go. So that's how you can graph. And then the last part of our thing was understanding that different forms help us look at different things. We kind of touched on that already. All right, so with that being said, we do have a different to-do list than the one yesterday. So now we're getting you back into the routine of like, your first priority is the lesson we just did. So scoring 80% or higher on the lesson 10 practice. And then you can continue to the other things. Like I know I have some people that still have the book it missing or their maze missing. If that's you, you know, you need the paper or something, you can talk to me, but like pretty soon I'll stop reminding you about these 2 things. But if your grade dropped to like a B or a C, that might be fun. We don't have those 2 things. Then if you're already finished with the first 3 things, consider correcting your quiz from yesterday. And then if I see that everyone's like not doing these things, then maybe you're done or I don't know, gave up, then we'll do a compute on something else that will help you. So questions on what we're doing. So today's task is the very first thing. So I'm giving you points for getting 80% or higher on the lesson 10 practice. Feel free to ask as you go, but I'll check in again like I normally do last 20 minutes or so to see what we are confused about. Yes. Yeah.
For this one, so we have to raise funds for uniforms and travel expenses. The soccer team is holding a car wash in a part of town with a lot of car and truck traffic.
The team spent $90 on supplies like sponges and soap. They plan to charge 10 per car, 20 per truck. Their goal is to raise $460. And how many cars do they have to wash if they wash the following number of trucks? So I've seen a lot of students just like, I don't know, do some scratch work math for each one. Really, if you made an equation, it'd probably make your life easier. But let's just move through it. So if they are washing 4 trucks, how much money are they making from that? It's $20 per truck. If they wash 4 trucks, how much money is that? $80 because you're doing 4 times 20, right? And then they want to raise 460. However, they did spend $90, so that already put them like in the negatives. So they're gonna have to actually make 460 less than $90 that they spent, if that makes sense. So I had to like try it both times without the 90 added, just to see what the question wanted. It wants you to factor in the $90. So 460 plus 90 is 550. So then if they made $80 from washing trucks, I'm gonna subtract that from 550. And what do you get from subtracting that? Okay, good, and I'm not gonna wash 470 cars, so. Check back, like they're charging $10 per car, so then I'm gonna have to divide that by 10. In order to get how many cars I would need to wash, which is what? 470 divided by 2. 47. All right, so that's literally what you would do for each one. The only thing that's changing each time is the number of trucks that were being washed. So like in this one, it's 15 times 20. So the cost to wash them isn't changing. So in that one, they are making $300 from that. Then you're still subtracting it from the 550. So you get 250 when you subtract it, and then you're still gonna have to divide by 10 to figure out how many cars you need to wash. So then in this one, how many cars do I need to wash? 25. So I've seen people do it like that, but really like the math that you're doing would be the same if you made an equation. So for example, they did $10 per car, so I would do like 10C plus 20 per truck. That's like 20T. And they want to raise 460, but then they had that $90 they spent. So really they want after that to have $550. Like you could plug in and then solve, or you could follow what like lesson 8 or 9 did, where if we're solving for cars each time, then maybe it might be easier to like just isolate the C. So in that case, you could do, so this could be one equation you made that maybe made the math easier. Or you could have done 10C equals 550. You could subtract the 20T from each side. And then opposite of multiplying by 10 would be to divide by 10. Which means then you have to divide the other stuff by 10. So then you could get that C is 55, because 550 divided by 10 is 55. Minus, and then minus 2T, because negative 20 divided by 10 is negative 2. And that should also get you the answers too. So then like, if I kept going, 21 trucks, I could plug into T into this one, that now makes it easier to solve for C. I could do 55 minus 2 times 21. And that gives me 8 cars, right? Did you guys put that for this one? Those of you that kind of work ahead. So like that could be another way that you do it. That might even be easier. Or just as long as you get to the right answer, I don't care. As long as it's not easy. So questions on that one? I know there's one more, but I'll leave that one as like a you try now that you saw me do like 3 of them. 3 out of the 4. Yes. All right, so let's look at the kindergarten one. So a kindergarten teacher bought $21 worth of stickers and cardstock for his class. The stickers cost $1.50 a sheet. The cardstock costs $3.50 per pack. This equation, so they're nice, they gave it to you, represents the relationship between all of that stuff and the dollar amount that he spent on the supply. So we're gonna, I'll rewrite it down here. So we're gonna complete the following to explain how we can tell this graph represents the given equation. So if we substitute the pairs of coordinate values of the points on the graph into the equation, we will have either true or false statements, which means those points are solutions to the equation. So if they are solutions, then plugging in these coordinates should make this equation true or false. We plug in points that are on the line into this. Would it make it true or false for it to be a solution? Good. So like, for it to be a solution, it would have to make the equation true. So even without doing the math, I could tell you that. Plus visually, like they're on the line, so that's also a way that you can tell if they're points that are on the line, then it would be true. Now, let me just double check, because I know we were figuring out if this could represent it, so let me see. The X would be the number of stickers. 1.5 times 0, we're plugging in this one. The C is cardstock, so that's 6. I know this times 0 is 0. Let's see if 6 times 3.5 is 21. And it is. All right, so far it's looking good, but yeah, it would have to be true in order for it to be solutions. Anyway, complete the following to explain what the vertical and horizontal intercepts, these should be in parentheses, by the way, mean in this situation. The vertical intercept of 0, 6 means that if the teacher bought no blank, he must have bought 6 blank. So an easy way to tell is to look at how this is labeled. What's on the x-axis? Stickers, so it's going in the order stickers, because it normally goes X, Y, but they're not using X. Those stickers, comma, what? Cardstock, because the C is on the Y-axis. So that's going second. If I'm going back and reading this, they bought 0 stickers. That's what was listed first. He must have bought 6 cardstock, because that's what was listed second. Everyone do that? Okay, so then this one, the horizontal intercept, also called your x-intercept, means that if he bought no, what is he not buying this time? He's buying no cardstock, so they kind of tried to trick you by flipping the order of what they're asking you, but still 0 means they're buying 0 of that, and if the 0 is listed second, so he bought 0 cardstock. That means he must have bought 14 sheets of stickers. Questions on that? I'm gonna check that this one's all marked the right way. Okay, yes. So it looks good. Questions on others? Time for like one more. Right? Okay, the hiker one. Okay, I remember liking this question. A group of hikers is progressing steadily along an uphill trail. The graph shows their elevation in feet at each distance from the start of the trail in miles. So first, what's the slope? How can we tell slope from a graph? Slope from the graph, anyone? Slope in general, there's lots of equations for slope, but I only showed you one today. Ryan? It's what? Well, it will tell you the steepness of it, but like, how can I tell the slope from a graph? I do what over what? Rise over run, okay, so that's slope. Slope can be represented a lot of ways, I'll tell you them briefly. It could be rise over run. It could be y2 minus y1 over x2 minus x1. It could be change in y divided by change in x, like lots of ways. I would use each one in like different situations. For graphs, I'd probably use rise over run. So I suggest find two parts of your line that you can see really clearly what those coordinates would be. So like maybe here and here. Right, I don't wanna pick like this one that I'm marking in green because I have to estimate. And that would mess up our numbers. So I'm gonna pick the two red ones, which are like right in the middle of the grid lines. I can really tell what they are. Highly suggest, if you can draw it, draw a triangle, otherwise, I know you can't draw on your computer screen. But then look at your rise. So if I'm going from 1,000 to 1,500, what's my rise? 500. So you have to pay attention to the tick mark with those frankly, you know, the replace. And then now look at the run. So if I'm going from 2 to 4, what's that change? 2. And then it's rise over run, so 500 divided by 2 is what? 250. All right, it's allowed to be a fraction, but it would just have to be fully simplified fraction. This one simplifies to a whole number, so that's fine too. So 250. Okay, that's our slope. Then it said, what does the slope tell us? So generally, the slope always tells you what it changes by. In like every slope intercept situation, slope always tells you what it changes by. So in this situation, it's saying that for every 1 mile that we travel, we are increasing by 250 feet. All right, so I will put that. It tells us how many feet the hiker's elevation increases, and I can really tell it increases because it's going from left to right. Like I can read going up. And for which equation represents the relationship? Both of these equations are in slope-intercept form. So what did we say our slope was? 250. Only one of these has a slope of 250. Is it the top one or the bottom one? Sorry if it's hard to see wherever you're at. Actually, it's the bottom. Because, and it might be shuffled on your screen, I don't know. But the slope always has to go in front of the x. That's a rule. So I could write it like this, or I could write it like this. But slope is always in front of the x no matter what. We said slope is 250. Your y-intercept, which is always your starting point. So like here, my starting point is 500 on the y. That's always a constant, like there's no variable attached to your y-intercept. So they try to trick you again by switching the order, but slope is always in front of the x no matter what. Now, it says, does this equation represent the same relationship? Does it? Yes, things like what can I do to this equation, which we said is correct, to get this one. So it looks like we move the 250x to the other side. You're allowed to do that, you just have to do it to both sides. So what do I have to do to cancel it on the right side? If I want. No, if I want it to completely go away and the 500 to be alone, how do I make that cancel out? Perfect. Well, not by 500. On each side of the equal line. So from the y, which then over here it cancels out, and then these are not like terms, when the next one July, so then we'll rewrite. Yeah. So, yeah.